Thank you. Hello, everyone. So I'm really going to be really excited to see how this talk goes, because I got asked to do it yesterday, and I said I would do a talk on the condition that I didn't have to do any preparation. So my goal is to teach you the Python object model, the method resolution order for multiple inheritance, and metaclasses in 20 minutes and have 5 minutes for questions left. We'll see if I get any of that. My name is Michael Foord. I've been a Python developer, for about 15 or 16 years, a professional Python developer for 12 years. I started my career in London working on a desktop application written in IronPython. There weren't many people using IronPython at the time, so I wrote a book, IronPython in Action. I caught the passion for testing, wrote a library called mock, which some of you might have heard of, and is now in the standard library as unittest.mock. And I'm now working, having made a few jumps via both Canonical and Red Hat. I'm now self-employed as a Python contractor and trainer. But please don't take this as too damning an indictment on my training abilities. OK, so can you all hear me all right, by the way? Yeah. OK, I will stop worrying. And can you all see the screens? Can you read the code on it? Is that good enough? OK, great. Right, so this is a very standard Python class. You can see the code there. We have an initializer, not a constructor. It takes self as an argument. So the object has already been constructed at this point. If you want to Python has two-phase object creation. If you want to override the constructor, the construction of the object, you need to turn off caps lock on your computer. And then you override new, which takes the self, and any parameters the same as init. And then should dunder new return, Tom, I'm sorry, I do get to explain dunder. The Python magic methods, the Python protocol methods that typically you don't call yourself, but the interpreter calls for you under certain circumstances. They start and end with double underscores. This is something that Python inherited from a C convention, and it makes them nice and recognizable. If you see a method starting with double underscores, ending with double underscores, you know it's one of the protocol methods, one of the magic methods, and you know that it's something that the interpreter is going to call for you, and typically you don't call them directly yourself. But double underscore new double underscore is a mouthful, and so I and some of the Python community like to call them the dunder methods. Dunder Mifflin. Right, so Python has two-phase object creation, and if you want to override the constructor, that should work. I didn't test this or plan this at all. OK. So long as dunder new returns an instance of the class or a subclass of the class, the initializer will be called. Dunder new is free to return whatever it wants. If it returns something that is not a subclass of the class being constructed, it will not initialize it. This is actually really useful. Mock makes makes good use of this technique. Mock objects allow you to customize their behavior, including customizing the behavior of some of the magic methods like a dunder get item and dunder set item, so that you can use a mock object as if it was a dictionary. Now, these magic methods, they're typically looked up on the class rather than on the instance. This is one slight area of confusion in the Python object model. So if I index, or technically subscript, into an object X there, Python is going to look up the dunder get item method on X, but it's actually going to look up. It's not going to look it up at all. There are fast paths inside the interpreter for that. That is how it's going to find get item. This means if you want to customize the behavior of dunder get item, you have to do it on its class, which if all mock objects were the same class, if you changed dunder get item on one, the behavior of every mock object will be changed. So what actually the mock constructor does is it creates a new subclass of mock or magic mock inside the constructor and returns an instance of that subclass. And then you're free to tinker with the class of the mock object, customize the behavior of the magic methods without interfering with any of the behavior of the others. So it looks something like this. It doesn't actually do it this way. and we delegate the actual construction to object. Let's see if that works. It's a long time since I've tried messing around with anything like this. So it was called thing, wasn't it? We should actually find our t is an instance of new. Not many use cases for doing that. Okay, right. So what I was intending to talk about is the instance attribute x here. We have an initializer which doesn't do very much. It sets the attribute x on the object, on the instance. And perfectly standard Python, when I look up the attribute x on the instance t, we get back the value 3. Actually, the full rules of how Python does that lookup are way more complicated than you might imagine, mostly implemented in object.dunder_getAttribute. Okay, so that's straightforward. We have an instance attribute, we fetch the instance attribute. What about when I do something like the also entirely astounding, tell me x. I'm looking up a method on that object. We get back an interesting object. But so let's take a step back and look at a bit about what Python objects are. So you've probably heard it said that Python is built on top of dictionaries. Dictionaries, hash tables associated with arrays, keys mapping to values. In Python, namespaces are particularly important, and namespaces are names mapping to objects. And we have an object here, and we have a set of names, some of which are valid, and some of which aren't. So along with this object, we have a kind of namespace that goes with it, which stores this mapping of attributes to the corresponding objects behind it. The corresponding object that the name t.x there points to is the integer object 3. So under the hood, and this is probably not news to many of you, there is an actual dictionary storing these attributes. And it's the dunder_dict attribute. It's not considered particularly private. There are lots of use cases for playing with this directly, particularly for working around the descriptor protocol. We can see this is a real dictionary. I can look up the x attribute, and I can do things like set arbitrary new attributes. And now my t object has a y attribute. So operations on the attributes of a Python object correspond directly is very much the wrong word because there are lots of slips in between. But it's not too much of a lie to say that they correspond directly to operations on the underlying dictionary. So this is what I like to call, when I've had a bit more time to think about what I'm going to say, Python from the inside out. This is not thinking about Python objects when we write classes, when we're designing code. Classes and objects, they're ideas. They represent something conceptually. It might represent a socket, it might represent a file, it might represent a worksheet in a spreadsheet. And we think about the object in terms of the concept it represents. And a well-designed object will have an API that corresponds as closely as possible to the thing it's trying to represent. If the idea your object presents and the way you work with that object map well together, it will have what feels like an intuitive API. But actually still, what we're working with is still Python objects, and all objects have the Python object model in common. So this is objects turned inside out. This is looking at their behavior from the inside. So that's straightforward. But you remember, mere seconds ago, I was looking up a method. And I'm pretty sure that my dictionary here has no tell me x entry. It's not there. So the attribute lookup is not as straightforward as just look at the object dictionary, find what's in there, and fetch the method. And in fact, it's not a problem because we know where that method lives. Every object In Python, we say Python is fully object-oriented. That means everything is an object. That means everything inherits from object. So what have we got? We've got our thing class here. A class is just an object. It's just a Python object. The consequences of this is if I ask Python, is thing an instance of object? It will say true. That will be true for anything you can find in Python, any first-class object. And this is not just theoretical. There's certain object behavior. You see that representation there? When you display an object at the interactive interpreter, you get a representation of the object, which includes the class name, some information about where it came from, an ID, which is a proxy for a memory location. That is actually the magic method done to repra, the representation. And it's inherited from object. There's a certain amount of behavior, including things like object.get done to get attribute, which implements the whole attribute lookup protocol, that your Python objects get just by virtue of being objects. That's what it means in Python to say everything is an object. There are some really interesting consequences of that. You can do really dumb things. So here I'm creating a list. It holds the built-in function abs, it holds the math module, and it holds the type error exception. And please don't ever write code that looks like this. Right. And it all does what you would expect. Ugh. And this is the bit where you're going to put your hands in your head. Exceptions are matched at runtime when the exception is raised. So Python will fetch the exception type it's looking for from the list. Everything is an object. Okay. Where had we got to? Okay, so I said that instance attributes are stored in the instance dictionary, but we can look up attributes which are not in the instance dictionary. So the rule for attribute lookup is, well, if it's not in the instance dictionary, where is it? And every object has a link back to its type. Everything is an object and everything has a type. Classes are just objects, and they also have a dictionary. And this is where class-level attributes live. Class-level attributes are attributes that are shared by all instances of the object. So you can have arbitrary attributes and methods. Now that we're in Python 3 and there's no such thing as an unbound method, methods are just functions that live in the class dictionary. Ooh, what's it called? What did I call that silly method? Ah, right. However, because I did this funny subclass trick, I get to do something like... there are many ways. This is the thing with Python. There's only one way to do it, is a lie. Okay, and you'll see I've just pulled out a function object. Interestingly, if I look up the method from the object, I get a bound method back. I get back something different. And this is, that's the descriptor protocol. Functions are descriptors. They have a done to get method. I'm not going to go into that. But what it means is when Python finds, via the attribute lookup, when it finds the method, what it does is it wraps in self and returns you a method where self is already bound in, partial application. So tell me x takes no parameters. However, if I do this, which gets me a function object, what's the first parameter? Self, obviously. You have to pass it in explicitly because we're working directly on the underlying function. So the rule becomes a little bit more complicated. First, we look in the instance dictionary. Then if it's not found there, we check the class dictionary. Not quite true. The descriptor protocol makes it more complicated. Okay, right. We don't have a lot of time left. Right, so metaclass is in 5 minutes. So the rule is you check all of the base classes up until you find it. The descriptor protocol overrides that, so properties override instance attributes. So if you just add the phrase, it's more complicated than that, to everything I say, we'll get on fine. Okay, right. Everything is an object. Every object has a type. Classes are objects. So what's the type of a class? What is its type? The type is its metaclass. And how do we instantiate objects? We instantiate our objects by calling their type. So how do we create a class? We create a class by instantiating its metaclass. And the default metaclass is type. And what will boggle your minds is that the type of type is type. Type is a type. Okay, so type is the default metaclass. Type is what creates classes. What you need to do to create a type is you need a name. You need a tuple of base classes. And you need a dictionary of members. And so there, I just created a class. This is what Python does under the hood. It executes when you enter a class statement, it executes inside the body of the statement, it executes the body of the class, creating the functions. That creates a dictionary of the mapping of all the class attributes, and then the metaclass is called with these things: the name, the tuple of base classes, and the dictionary of attributes created from executing the class body. This means that that class body is a very interesting scope that doesn't behave quite like other Python scopes, and I'm not going to go into that. What it means, so that's a metaclass in use, a class factory. I don't think I'm going to get to the method resolution order, probably. So the typical way to create a new metaclass is you just inherit from type. You override whatever behavior it is that you're interested in. So here I'm underriding done to get item on a metaclass. Now we have in Python this funky syntax. Is it metaclass equals? Now, there's nothing inside the body of the class. Because I've set a metaclass, as long as I've remembered the Python 3 syntax correct, Python is actually going to call my new to create the class. Now, I could have made that more explicit by putting something in the call. But the interesting thing is, remember when I said earlier that the protocol methods are looked up on the class? So here we have an object. Its type is new. When I subscript it, the type of foo is new. Done to get item on new is going to be used. So here we're getting behavior from the metaclass on the class object, and the metaclass is not in the inheritance hierarchy, which is an interesting corner of the Python object model. It's interesting to note that class decorators and dunder init subclass particularly are good reasons to never write a metaclass. But this is the machinery that's at work under the hood. Everything in Python is an object. Every object has a type. Classes are objects. Their type is typically type, the default metaclass, responsible for creating types, but you can override that, and there are many reasons why you might want to override that, but I can assure you far more why you might not want to do that. Okay. I hope that was understandable. We're going to be coming up for question time very shortly. I did promise, let's look at the method resolution order. So the attribute lookup order that I mentioned before, first look on the instance, then check the class, and then maybe check any base classes until you find the attribute and it's returned. That's straightforward in the presence of single inheritance. But here you can see I've got a class A, a class B, a class C. A and C both define a foo method, and class F inherits from D and E. When I instantiate F and call foo, what is going to happen? Which foo method is going to be called? The fact that it's even slightly annoying to work out is another reason why you shouldn't use multiple inheritance. Mixing classes are the only valid reason. So in this case, it was actually the A that happened. Instead of taking questions, what I think I will do is I reckon I can possibly explain that in 5 minutes. Let's have a look. So F is a class object. We've explained that in the face of inheritance, Python has to walk up the inheritance hierarchy in order to find the method. How does it do that in the face of multiple inheritance, where you have an inheritance graph? And the answer is that Python constructs a method resolution order, the MRO. It linearizes, and the algorithm is actually called the C3 linearization algorithm. And I'm hoping I haven't talked too much nonsense. If Mark is at least not scowling at me, I'm not doing too badly. And this is a linearization of the method resolution order. Python will walk up until it finds the first one. What this means is it's perfectly possible. Oh, right. How does it construct? What is the linearization algorithm? The linearization algorithm has essentially 2 rules. The rules are that children must be checked before parents and that order must be preserved. So in this example, D should be checked before E, and D should be checked before B, and B should be checked before A, because children must be checked before parents. Okay. What it means is it's perfectly possible to create inheritance hierarchies, convoluted inheritance hierarchies that aren't possible. So if I reverse the order of these and have E and D, you'll see an exception which you will hopefully never see in practice. Oh no! Ooh, what did I do? I'll make it easier. I'll put A at the front rather than spending precious seconds debugging this. Right, type error cannot create a consistent method resolution order. The 2 rules that I described are that children must be checked before parents, but that the order they are declared must be honored. Having the order they're declared honored is useful because it means you can have a mixing class that you mix in via multiple inheritance. The only good reason to use multiple inheritance. And you declare it first, and your overridden one will always be called before the main class. And you use super. This is cooperative multiple inheritance. If your mixing class uses super to make the call up the inheritance hierarchy, super will actually jump sideways, because the method resolution order, in order to honor these, children must be checked before parents, and the order matters. You will often find that the next in the method resolution order is not up the hierarchy, but a sideways jump. That was fairly disorganized, but I think we maybe kind of got there. Thank you very much. Do we have time for any questions?
We have time for 1 or 2 very quick questions.
I hope it's quick. Abstract-based classes and meta classes are usually considered black magic.
Yeah.
Arguably they are. So my question is, do you believe the Python programmers should leverage them, use them, or avoid them?
I think it's very useful to understand them, because you're understanding Python. It's the same with the instance dictionaries and the lookup rules. It's useful to know when you do foo.x, it's useful to know what's happening if you want to understand. And similarly, when you instantiate a class, it's useful to know what's happening. So it's no, not something you should leverage, particularly, but something that's worth understanding.
Well, we have one of our speakers who wants to ask a question.
Thank you very much. That was. Can you hear me?
I can hear you.
Yep. That was entertaining and illuminating. I have a question about the attributes of the object which you showed correspond to a dictionary.
Uh-huh.
But a dictionary is itself an object. So
Right, yes, yeah.
how do we get
Objects
started?
all the way down. I guess you could say that it finally ends in type, where if the type of type is type, what creates type? And the answer is somewhere the interpreter has to cheat, and it creates a C struct and pre-populated, and type is never instantiated. So, you know, there is a bottom to the house of cards.
So please, let's everybody thank Michael. It was extremely great talk. Last minute live demo worked perfectly. So thank you.